Okay. Okay.
Hello, everyone. Can you hear me? Okay, good. So for tomorrow, the happy hour, everyone is invited to go. Okay. Uh, if you are a student, you didn't pay yet, it's not a problem. You can pay the double after the meeting. Sorry about that. Just kidding. So if you are a student, you cannot pay, it's not a problem. Okay, we can cover you, but everyone's invited. Okay. Yes. So put your name, or ask the lady in the help desk to put your name in the list. Okay. You need to know the number of person to go because we will rent a car. Okay, to transport you go and back. All right.
So we are not really starting now since it's still 1 minute and 41. Not yet. So yes, I'm the feeling I have to entertain you already now, but there's no longer music, so we can test everything. Yes, I know. I just tell that this is before the beginning. So and otherwise I have to be there. Since it's very bad for the guy if I walk all the time, and I will not do that. But let's wait until recording is going to start. Okay, shall I start, Raimundo? Okay, so it's me again.
Paulinho, ainda vai ter a contagem ou já pode começar? Pode começar? Ok.
Okay, it's me again, but I have to warn you, this is some other subject I did be. So it's not in the series I gave about hypersurface singularity, since this is a talk in the series F4. And at that moment, Mihai Tibar should give the first lecture in that series. And he gave the slot to me and he said, Dirk, do anything you like, but it must be about real singularities and a kind of application of things we do in singularity theory. So that I'm going to do, and so it is completely unrelated from the things I have been said before, up to perhaps you will find out. Okay, so this is talk is about the area function on polygon spaces. So on the blackboard you see a polygon, so a set of intervals and a set of vertices, and where we are going to look especially at the area function on this polygon. So let's take the first slide. Okay, you see here the pictures, and there is a way to define area. So you take just the coordinates of the point in the Euclidean plane, and you take all these determinants. So somewhere there is the origin, which is not written there, and then you see that that this. Okay, I have to use this guy. This expression tells you the area of the polygon, but it is signed area, and that means that at certain moment things can also come with a minus sign, and it also, if things are double, then it is counted double. And it's not area, but it's 2 times the area. But I always never write 2, so I call this area. And I will study this area function with several type of constraints. First, we take all the edge lengths fixed, and this is called linkages. Then I fix the total lengths, and then in the last section, I don't fix the lengths, but I fixed all the vertices. They have to lie on an ellipse or circle. Okay, so I fix just first thing I'm going to do is that, so the space of polygons with fixed lengths, edge length is given by ML. And then this area, the question is, when is this area function a critical point of A, of the area? When is a polygon a critical point of the area function? And we will find out what is going to happen. Just escape. Okay, let's try to do this for the foregon. So I have foregon. So this happens if you walk with you use your own computer, which is not on the network. We're going back to the original slide, I hope. Yes. Okay, so given are the 4 sides, A, B, C, and D, they are fixed, the lengths, but so there's still a one-dimensional movement possible. And to compute the area, you do your high school or calculus formulas. The one triangle has area AB sine alpha, and the other CD sine gamma. And then there is a constraint. The constraint is that this diagonal can be computed both from one triangle and from the other triangle by the cosine rule. So now you compute your critical points with Lagrange multipliers. So you get this matrix, it's just calculus, and you find that sine alpha plus gamma is equal to 0. And this means that as alpha plus gamma 0 is mod pi, that these 4 points lie on a circle. High school geometry. Okay, so the proof for 4 points is easy. So for 5 points, it could be more difficult. But there is a nice trick. If you have 5 points, like here, you fix one of the small diagonals. So this triangle is now fixed, and then there are 4 points left. And then the area function has critical points if these 4 points are on a circle. Okay, but now we fix some other small diagonal, and we find again 4 points on a circle. and they have 3 points in common, so it's the same circle. Okay, and this proves the statement that where is this statement? That this area function is critical if P is a cyclic polygon. Okay, I should say that this work I'm talking about has been done together with George Skimshashvili from Tbilisi and Gayane Panina from St. Petersburg. Okay, and we also managed to compute Morse indices. And I'm not telling them in this lecture, since I have so many things to tell, that I only, the message is we computed them. You can even compute them from this kind of pictures. And the Morse indices, they are in the terms of these pictures written in easy formulas. Okay, this is what I wanted to say about linkages. So the fixed, all the lengths of the sides were fixed. Okay, now is my first real application, so to say. I take now only the sum of all these distances given. So consider you have a rope of a fixed length, and you have certain pins, and you want to have these straight lines between the pins. But you are allowed to change the places of the pins and the lengths of the intervals in between, as long as the total length is constant. The total length is given by the perimeter. And so this is the sum of the lengths. And so in certain sense, we have on this configuration space, have two functions. We have perimeter and we have area. And the perimeter of a polygon is always positive, but the area can also be negative. And in the intermediate set is where the area is 0. Okay. So let's give some examples of special cases. We call a regular star a polygon which is all side lengths equal and is regular. So all the points are on the circle, on the angles are the same. You can also have stars. So this is a usual regular polygon. This is a regular star, and this is also regular. There, all this is 1, 2, 3. This is a 6 cone, I think. It's 6, 1, no 7, or I think 7 gone. And no, I don't count the number of points, but they are all regular. But you can also orient them in the other direction, and then you find similar pictures with winding number, the opposite of the other winding number. This is winding 2 times around. Then in the next picture, you also see something else. For even number of vertices, you can also have the complete fold. So this is 1, 2, 3, 4, 5, 6, 7, 8 cone. Clear? Okay, now the statement is that the space of polygons with fixed perimeter is homeomorphic to the complex projective space. Okay, that was familiar from this morning even, and from yesterday. But that had nothing to do with that. We have a function area, and we will prove that it is a perfect Morse function. About that more. And the critical points which are given are regular starts and complete folds only. And we have formulas for the Morse index in terms of the winding numbers. And the critical values increase with the Morse index. So it's a very nice situation that reminds you on perhaps on the well-known Morse function on CPN, which has the same properties. But this is not that function, but near to it. Okay, let's first prove that this configuration space is a projective space. A question.
What is a perfect Morse function?
A perfect Morse function, that's a good question. That's, you should always say that, but it is a good question. So in the Morse theory, there are Morse inequalities. And in fact, the number of Morse points is always bigger or equal than the Betti number. And if the Morse indices, if the number of critical points and their indices, they just correspond to these Betti numbers, then this is a perfect Morse function. So if this is on the projective space, then you have only in this complex space, only in even dimensions up from 0 to 2n minus 4. Okay, the way to get this is to parameterize, take a first point and take the directions from one to the next until you are in Pn. Okay, you start with that. Then the next what you'd say, okay, I put this set of lengths, this set of vectors as a point in the projective space. And that's all. The only thing to show that it is homeomorphic is that you have to find a map back. And what you take is just representatives, and you divide by the parameter function. And then at the end, the parameter is again 1, if it was 1 in the beginning. And in fact, what you're doing is you do this up to translations and rotations. Rotations is multiplication with a complex number of absolute value 1 in this business. And since the total length has to be fixed, you have no scalar multiplication. And why it's not diffeomorphic? Because parameter has square roots. That's also the reason I wrote this. And that means that you have two choices, or you can give it the smooth structure from the projective space, or you can take a topological structure. We take the smooth structure from the space, and that means that our area function is no longer differentiable in all points. As soon as a square root appears, and square root appears at the moment that at those moments that 2 points coincide, 2 or more points, then you have a non-differentiable situation for the function. And we will deal with that. Okay, you can also, if you take in the same problem the quadratic distance function, you don't have that problem. And then in certain sense, you get this usual function that people, that you find in textbooks about Morse functions. Okay, now we have to prove, to find out what the critical points are. Okay, we first take a situation that L1 and L2, these two lengths, are different. Remember, the point P2 can still move, but we freeze all the other things. All the other lengths we freeze for a moment. So we're looking to a kind of partial derivative, so to say. And then we still have that the length of this, the distance to P1 plus the distance to P3 has to be constant. So this is a point on an ellipse. And when is the area of this triangle maximum? If and only if L1 is equal to L2. So you have, in this way, you show that all these side lengths are equal, have to be equal for a critical point. Okay, and if they are all equal, then you can also use the other statement that they have to be on a circle, and They form a regular polygon. Okay, this proves more or less the statement that we know exactly what the critical points are. All these regular polygons, regular stars, only forget to test what happens at the non-differentiable points. Okay, this is difficult since there is not a derivative, but there is something else. Don't read this text completely for the moment. This is only the word Clark differentiable, subdifferentiable. You can do, there exists a differentiable which has not a value in a vector, but in a cone of vectors. And you can work with that idea and show that in the points where we have non-differentiability, there is no critical point from the point of topology. So for topology, this behaves as a regular point. Is it a perfect Morse function? Okay, so we know that we have n-1 Betti numbers all equal to 1 in the even dimension, and in the odd dimension they are all 0. So we have the right number of critical points. So we can exactly count the number of stars, and they exactly count up to n-1. So this number is minimal, and it's equal to the sum of the Betti numbers even in this case. But this does not prove completely that they are all Morse. So this was a delicate point, and so we had to do something more, and we were able to solve this by rather ad hoc arguments, since formulas did not work. And then a student of Panina completed the result. Okay, so this was the fact that we showed that we have this perfect Morse function. Okay, and the in itself is, so I think we showed now everything, since you could compute these indices at the place where were necessary. And so all these statements are more or less proved or easy to prove now. Okay, so this was first application, and a small paper of us that we showed this the Morse functions of what we call the rope. Since second part of this talk is that we have now two functions, area and perimeter, on the same configuration space, and so you can fix area and you can fix perimeter. So there are two different problems. One is to look to the extremal values of area on perimeter constant that I've been doing. And the other is you to take area constant and you want to extremal value of the perimeter. And in optimization theory, the isoperimetric duality was well known, that the minimum of P correspond to the maximum of A. And our goal was to extend this to all critical points, and even to the level sets of A. So the level sets of A, they are subspaces of this complex projective space. Okay, what are we going to do? We take the map from C to R cross R. So we take the two components, P of perimeter, A of area. Just like we did yesterday in the complex geometry, we took a function f and we took a linear function and got a map to C2. Now we have a map to R2. And also here we have a discriminant, the critical set. And the critical set, you can compute that, consists of finitely many curves. Good to remember is that area function is second degree and perimeter function is more or less first degree. So if you if you multiply with a parameter, then with a positive parameter, then the parameter, if you multiply the situation with a positive parameter, then the parameter is multiplied with that value. And then, okay, so in the case of homogeneous singularities, of homogeneous functions, all the critical sets are lines. If you put quadratic to linear. And moreover, you have a discriminant set which give you all quadratic relations between area and perimeter. So area is equal to perimeter squared, since area is first degree and perimeter is area is second degree, perimeter is first degree. And okay, here you see the pictures downstairs for n is 5, 6, and 7. And so these are the discriminants, so to say. And in between, you have the smooth things. And outside the discriminant, you have a locally trivial fiber bundle. And so this is, in a certain sense, the music is the same, but the situation is different. And what we remember is that if we put here a vertical line and fix this vertical line, then at that moment you have fixed the parameter, then we know exactly the critical points. The critical points are just here. This is the regular one. This is a regular star with winding number 1, winding number 2, winding number -2, -1, 0. So we know exactly here the critical points. Regular fibers are, yes. Singular fibers, they have a Morse singularity type. Since the homogeneous property, you can move, the singularities are all the same along this curve. Okay, so this is similar to the surf diagram. This is just a picture I explained before on the last slide. Oh, just have a look what is coming. Yeah, okay. Okay, now I will make a homeomorphism between area constant and parameter constant. In two cases, one case is the area is positive, in the other case it is negative. So we are going to construct maps from one to the other. And this is quite easy, since I learned from singularity theory that it is in such a discriminant, you can travel from the vertical line to the horizontal line. And you can just follow the critical things, and you can also lift this lift this vector field upstairs, and you get just a map from everything above this vertical line to everything above this horizontal line. This is real. So all what you see is real. And so in the complex case, in this picture could have different intersection points. In fact, here they have also a second intersection point with the area minus something. So what you really move is one situation to the other. So you have the whole statement about fixed perimeter to fixed area, and they move from one to the other. So the critical points are the same, and the level curves are level curve foliation is also identical. And then we have the statement over here. The critical points of P are exactly the same as the critical points of A. And the Morse indices, they are opposites, so to say, in the case that the area is positive, and they are equal in case the area is negative. Okay. Any questions? Yes.
So in this last slide, I understand lowercase m of p stands for the Morse index.
Yes, and if of yes, and the small m and the big m is the p is the polygon.
Yes.
Yeah. And the small is in case of areas, I think, and the big is in the case of perimeter,
I see.
or the other way around. So I don't.
Yeah.
Yeah.
Okay, thank you very much.
Okay. Now we go to the third and last application. Okay. So you also know, let's say something, you also know the cell structure now, and you know that the homology groups are exactly the same as the homology groups of the projective space. Third section is about circular polygons, which is in fact quite easy in the beginning. So we fix all these points, and they have fixed them to be on a circle. And lengths, they are arbitrary as long as the points are all on the circle. And then we take the angle between from the origin. I hope I have a picture. Do I have a picture of that? Okay, so if you have the points over here, P1, P2, origin, then this is alpha 1. And then alpha 2, alpha 3, they can be also negative if they go back. And the area is just the sum of the signs of those functions, if they take circle with radius 1. So then there are several situations which were defined on the slide I moved away, since the pictures tell better what it is. You have regular polygon on the circle. All the sides have to be equal in this way. And a regular star, this is a 7-gon, this is the same thing for an 8-gon, and this is also 8-gon, since you go 2 times around. This is also 8-gon. This is some regular 8-gon in star form. This is also 8-gon where you go up and down. And here you see for a 7-gon, but with a zigzag in it. Going. So these are in fact 3 sides. 1, 2, 3. And this is also a 7-gon with 2 zigzags. And then we will, so in all these cases, they are supposed to be regular. Here I have something I called zigzag train, since what I do is I take an arbitrary length here and the same length over there and go back. So I have a 4-gon, and this is a 4-gon which I can move by taking the lengths equal but larger or smaller. In these cases, I cannot move, keeping this property of having all angles equal. So these are just the situations where all the angles from the origin are equal. So the names are defined here, so you can read that in a handout later. And we go to the statement that what you have seen, the first, you have a critical point of all these A's are angles in absolute value are equal. So they can continue, but you can also go back if you want. So all these stars, and they're all critical points, Morse type. And you can compute the Morse index by looking to forward and backwards. So forward, backward, you have in this kind of zigzag business, and you can compute them exactly. And then there is something which is degenerate star, and I had to tell this to you in this picture. I did not explain this picture. Do you see an 8-con there? Yes, I see. But 8 points altogether. This is the degenerate 8-con. And that degenerate 8-con is non-Morse. It has a Milnor number, and the gradient map has a local degree. For Morse points, the local degree is always -1 or +1, but here it's something else. It is non-Morse. And in the case that n is even, you can have non-isolated singularities. This was the case of the zigzag train. Then you can move. But in the odd case, all singularities are isolated. Proof is sit down and do the computation with this function A is the sum of all signs. And just with a very elementary calculus course up to the Hessian, you get the result. Okay. And then about the degenerate star. You did not get the result of that in that way. You know it's a singularity. This is its formula, the 3-jet. And from there you can compute its Milnor number. If n is odd, this is an isolated singularity. And then there is a way to get its index. Since you know that the configuration space is a product of circles, has Euler characteristic 0. You know all the other critical points. And you know their indices. Okay, then you take the difference with 0. So, and that is your index of your critical point. And then what you have to do is to count everything. The n over b was also the number of different things depending on the amount of zigzags. And you find this binomial expression which is this sum is equal to that. So this is a good exercise for the first calculus course. And if you do this for n equals 7, you can list all these things. The degenerate star, you wait until the end, that you did everything, and then you count up, and then you put in -20 to get 0. Okay. But if you think about what you have been doing, then the calculation is rather difficult. So it is easy to forget something. So why should this answer be okay? There are 2 reasons. One is it's a geometric problem. And you can test the answer easily in if m is a low number, and it is okay. And the second reason is that in the geometrical problem, you always end up with a nice formula. But I was not completely sure about this. I want to have a kind of test. And the test consists of a system to compute the signature in cases of functions, real functions with isolated singularities. And because this is about real singularities, I want to explain this and to show that in this context. What you have to do is you start with the Milnor algebra. What is the Milnor algebra? You take all the set of all holomorphic functions, or power series if you want, and then you take the Jacobian ideal, the ideal generated by the partial derivative. That's called the real Milnor algebra. We also need the Hessian determinant, HF, and we will see that as a class in the Milnor algebra. And after that, we will take any linear function which is positive on this class. And then what we need is to define a function beta, which is a multiplication between the functions in this ring. And the Eisenberg-Levine-Kempf-Jasmine formula tells you now that the index of the gradient is equal to the signature of this matrix. So in fact, this is, if you can compute Milnor algebra and this multiplication, you are able to compute this. Perhaps this is or can be implemented in some system. Okay, what we are going to do is to do this algorithm. So we study our function and we make the Milnor algebra. And I will write down in the beginning what you're going to do. If you have this function, low dimensional, for the Milnor algebra, you have to compute df dx and df dy. In fact, this function is minus 3x1 squared x2 minus 3x1 x2 squared. If you had only power 3, if you had only 3, you make this picture of the Milnor algebra. And then you say, okay, the derivatives are these coefficients. So for this Milnor algebra, O modulo JF, I can use as basis 1, x1, x2, and x1, x2 as transversals, so to say, to the Jacobian ideal. If you take this function, then it turns out that this function has not this Jacobian ideal, but you can use the same transversal. But if you use the same transversal, then the point is that if you have x1 squared in some computation, you have to see that it is equal to something like this, a multiple of that, and x2 squared is also a multiple of this. You can see this by differentiation. So you get the vector space is, so to say, the same, but the algebra structure is different. What you have to do next is to make the multiplication algebra. You have these generators, and I've put them already here. x1 squared, x1, x2, x1 squared, x2, and here I have x1, x2, and here I have x2 squared. This is degree 2. I'll make this picture. Here I find things of degree 3, and here I find things of degree 4. So this is the multiplication algebra, and in fact you see that this Milnor algebra, the generators, you get transversal generators, they are monomials without squares. Since if you have a square, you can change this in something else. Then you get a big matrix. This is a smaller version, depending to the degrees of this multiplication. So this is the middle. And then you say, okay, I may choose my function L, and I choose my function L in such a way that this function L is only non-zero on the place where the Hessian is, and this is over here. So I get in all other places degree not equal to the middle degree, I get zeros. And now I have to compute the signature, and I do this in the following way. I have this, but I remember that the situation is symmetric, so to say. So the signature of the whole matrix is equal to the signature of this B22. So now I have to do B22, and the multiplication is determined, I take monomials, and then it's determined by the number of elements, indices in the intersection. So this means that I come to a combinatorial question. I have a matrix where the elements are indexed by the number of elements in the intersection. Okay, and that means that if here I have x1, x1, then the intersection is 1, and then they all have the same number of intersection points. These all have the same number of intersection points. So there were here 4 different colors. So the intersection between the indices can consist of 0, 1, 2, or 3 elements. And this is 1 dimension higher. And I still want to be the signature, so I have to compute eigenvalues. And I did that by hand in a quite elementary situation. But then it turned out that the things became more difficult. And then we did not finish the paper completely, but the referee sent us a message for you can do this for any number of vertices if you apply Schur's lemma and Young's rule. Now, we did that, and we got this as eigenvalues. Oh, rather complicated. And now to see how many positive or how many negative there are. And moreover, so it looks easy if you take some low-dimensional things. But we still have, we know the eigenvalues, but we still have to fill in, so to say, the relations which is between the B1s up to the BNs. And this relation is there, that these numbers, they are one-dimensional and they are related in this way. So the end is now that, okay, you have to substitute BP in the formula which was here the BP. So it's still more complicated. And what you need then is to find that this complicated formula is equal to that easy thing you did before. And we found a kind of algorithm which we put some formulas in it to find the recursion. And I have still time, well, since I started later. Yeah, but I'm almost ready. And if you do this recursion, you could find that you got an elementary complete reduction. So the eigenvalues, they turned out to be quite easy, all the same sign. So that means that the index is just the dimension of the space or minus the dimension of the space. And at the end, you can conclude that this is really the index. And this coincides with the topological question you did before. So why I'm going to show this One reason is to tell you that this Eisenbut-Levine-Kinshasa formula works. The second thing is that doing singularity theory brings you sometimes in areas you have never heard about, or heard about, but never understood details, and then you have to use it. And in this time, it was very nice that I had a roommate, a colleague, who understood something about representation of groups. So we wrote together a paper about intertwining representations, which gave at the end these formulas. Here you find part of the literature, and I thank you for your attention.
Just as a curiosity, have you tried doing something similar with a volume function? So taking
We try to do something with volume functions, but volume function is much more difficult. So what is the signed volume of so if you have just a cube, you know what the volume is. But if you have a kind of thing which is going back and up and down, then you have difficulties in defining your volume. Okay. Okay.
No, it's not necessary. It's not necessary. No, it's okay. So we can begin. Firstly, I'd like to thank the organized committee for the opportunity to talk in the school. My talk is about the bifurcation values of real polynomial mappings. So the plan of the talk is the following one. Firstly, we remember the definition of bifurcation set of real polynomial mappings. And in this talk, we discuss about two regularity conditions at infinity. So we begin with the following definition. Given a polynomial mapping, we say that T0 is a typical value of f if there exists a neighborhood U in Rp of T0 and a homomorphism H, there exists a neighborhood U of T0 in Rp such that the restriction of f to the pre-image of U is on fibration. Fibration here means, okay. So we say that T0 is a typical value of f if there is a neighborhood U in Rp of T0 such that the restriction of f to this is a C infinite trivial fibration. Trivial fibration means that there is a diffeomorphism H from this product space to the pre-image of U such that the composition with F is just the projection on the second component. In other words, T0 is typical if there is a neighborhood U such that and a Homer diffeomorphism H such that you have this commutative diagram. With this definition, we say that T0 is an atypical value of F if the control occurs in the previous definition. And we denote by BF the set of all atypical values of F. In particular, from the definition of definition 1, we have that all the critical values of F is an atypical value of F. So it's found by the definition 1 that all critical values of F is on bifurcation, is on a typical value of F. Here, Sing F is just the critical points of F. In particular, the bifurcation set is just the union of all singular values of F with the regular values of F, which are atypical values of F. Now, just two examples and some computations. You remember here the example from Brofton. So we'll consider F defined as follows. Then we will show that 0 is on a typical value of F. To do this, you consider the positive numbers in the real, we denote by U1. And if you consider the diffeomorphism H as follows, then the composition with F is just the projection on the second component. This means that all positive numbers is a typical value of F. With the same H, we can show that for any negative numbers is a typical value of F. And since the fibers in 0 and the fibers for any t are not diffeomorph, then we conclude that 0 is a typical value. Consequently, the BF is just the 0. Now another example for mappings. Sorry, in particular, this example shows that regular fibers of F may contribute to the set BF. In other words, BF minus the critical values of F may be non-empty. One example, a mapping example from the work of Ha Hui Hui, Negui Tat Teng. You consider the following mapping from R3 to R2, defining as follows. Then we will show that the origin in R2 is not on a typical value of F. So to do this, we consider the bow of a radius R centered at the origin R2, and the diffeomorphism H defined as follows. Then, if you consider composition with F, you can compute that and see that this is just the projection on the second component of this product space. From the definition, this shows that the origin is a typical value of F. In other words, 0, the origin of R2, is not in BF. As Cesar said yesterday, on complete characterization to BF is an open problem. In fact, we have incomplete characterization for a special case only. We have incomplete characterization for the bifurcation set for K2, for polynomial maps from K2 to K. In the complex case, this follows from the work of Suzuki, Han, and Le. In the real case, from the works of Tibar Zaharia and Costa de la Pointe. And more recently, for mappings from Kn to Kn-1, from the work of Joita and Tibar in the real and in the complex case. In other class, this is an open problem and a difficult problem to obtain a characterization to the bifurcation set for polynomial mappings. Just some words here. If you take a polynomial map from Rn to Rp and you consider a regular value of F, then we can use the Ehrenmann theorem to show that it's possible to find positive constants, delta and R, such that this restriction inside the bow is on vibration over a small neighborhood of T0. So to decide if T0 is a typical or a typical value of F, we need to see outside on compact set. It means at infinity, the behavior of F at infinity. So one approach to describe the points in BF is through appropriate regularity condition at infinity. The idea is under a regularity condition at infinity, you can define a subset in Rp in order to obtain a vibration for F outside this union. In other words, under a regularity condition at infinity, you can define an infinity F and try to show that the bifurcation set is a subset of an infinity F with the critical values of F. Moreover, it's natural to ask about the structure of an infinity F. You ask if an infinity F has properties which imply a good approximation to the bifurcation set. And we expect that the regulatory condition defining an infinity F is not too strong. In this talk, we focus in two regulatory conditions at infinity for polynomial mappings. We consider Rabi condition and the Kurdyka-Simon theorem, and the row regularity condition at infinity. Firstly, we begin with the Rabi function. So given we denote by L, R, N, Rp, the set of linear mappings from Rn to Rp. Then for NA linear mapping from Rn to Rp, we denote by A star, the adjunct operator of A. Then we define the following function. We take a linear mapping from Rn to Rp, and VA is just as follows. We take the infimum of this set, or varph is a linear mapping from Rp to R, and we consider composition of the adjunct operator of A with varph, and you take this infimum. From the works of Gaffney, Kurdyka-Simon, and Jelinek, they use equivalent functions to V. Equivalent functions here means the following. We see that two functions defined in the linear mappings from Rn to Rp are equivalent if there exists positive constant, CD, so that V1 and V2 satisfies the following inequalities. For instance, we will present a function equivalent to the function V, called the Kuo function. So given a linear mapping from Rn to Rp, we denote by at I the gradient of the coordinate function of A, and we define the Kuo function as follows. The Kuo function is defining the linear maps from Rn to Rp. You take A, kappa A is just the minimum of the distance of at I to the vector space generated by the vectors nj with j different of I. Then from the work of Kurdyka-Simon, kappa and V are equivalent functions. So you have just an example how you can compute the kappa function, for instance, for linear mappings from R3 to R2. So given a linear map from R3 to R2, kappa A is just the minimum, where here eta 1, this is just the cross product of the vectors eta 1 with eta 2. Then you take the minimum. This is just the kappa A. With these functions, we can define the set K infinity F. What is this? If you consider mapping from Rn to Rp, K infinity F is the point in Rp such that it's possible to find a sequence in Rn such that the limit of this sequence comes to infinity, the image by F for the sequence comes to T, and you have this asymptotical behavior here. Here is the function, the Rabi function defined previously, and you can also use any equivalent function to V to define the same K infinity F. For instance, you can use the kappa function here, and you will obtain the same set K infinity F. This set is useful to study the bifurcation set by the next theorem. from the work of Rabier, Gaffney, and Wieland, given polynomial mapping, then the bifurcation set is a subset of the critical values of F union with the K infinity F. And also from the works of Kurdyko-Simon, given polynomial mapping, then the critical values of F union with the K infinity F is on closed semi-algebraic set of a dimension less than P. In particular, from this theorem 7, this set has measure 0, and for instance, for P equal to 1, this set is a finite set. In other words, this set is a good approximation to the bifurcation set, since it has measure 0. The inclusion in the theorem 6 can be proper by the next example, for instance. You remember the example 3? If you take F as in the example 3, then you have shown that the origin is not on bifurcation point of F. Then you can show that the origin is in K infinity F. To do this, you consider the following sequence, phi t. Then, with positive t, when I apply F in this curve converges to the origin. F applied in the curve converges to the origin of R2. The limit of the norm of phi converges to infinity. And we can compute the kappa function in the Jacobian of F at phi. When you compute the kappa in the Jacobian of F, you have this expression. And when you take the product here of the norm of phi with kappa, this converges to 0, directed by these equations. So, by the definition of K infinity F, the origin of R2 is in K infinity F, and the origin is not in BF. In other words, the inclusion in theorem 6 can be proper. Now I will discuss another regularity condition we call Rho regularity condition. To define this condition, you take a point in Rn, we fix a point in Rn, and you denote by rho A the Euclidean distance function to A. Rho A is defined as follows. Then we define the following set with rho A. Given polynomial mapping, we fix A in Rn. Then we denote by MAF the critical locus of F rho A. And you call this set of the Milnor set at infinity of F. On example, how you can compute this set. For instance, you consider the Broftel example. Then MAF is just the zero of the determinant of the here of this matrix. This matrix here, the first line is just the gradient of F. The second line is the gradient of rho. And MAF is just the zero of this determinant. MAF is just the point in R2, such that this equation is equal to 0. With the set MAF, you can define SAF. So SAF as the setting RP, as a subset in RP, so that there is this sequence in MAF. The limit of this sequence comes to infinity, and the image of this sequence comes to T0. You call this set SAF, the set of asymptotical whole array non-regular values of F. And with this set, we define S infinity F. S infinity F is just the intersection of all SAF with A in Rn. The relation with the previous set K infinity F is given by the following theorem. So if you take an analytic curve in MAF, such that the limit of the sequence, the curve comes to infinity, and when I apply F in the curve, the limit comes to C, then this limit converts to 0. In other words, C, if you take a point C in SAF, then C is in K infinity F. In particular, SAF is a subset of K infinity F, and when you take the intersection, S infinity F is a subset of K infinity F. Okay? The idea is to give some steps of the proof of this theorem. So to do this, we remember the definition of cap V here. Just a second. Is here. V is just these functions, like that. So the idea is to give some ideas of the proof. Let's see. So you fix C in SAF as in the theorem here by the hypothesis, and you denote C by C1 until Cp, and we assume that 0 A is equal to the origin of Rn, okay? To simplify the proof. Then, since the curve phi so since phi is MAF, this means that the rank of the matrix, we remember that MAF is just the critical points of the mapping F rho here. MAF is the critical set of the mapping F rho. Then this means that phi in MF, the rank of the matrix, that the gradient of F1 and the gradient of Fp and the gradient of rho, the rank of this matrix is less than P plus 1. Here. This means that there exists, the rank is less than P plus 1. This means there exist constants here for each t. Here for each t. The gradient applying in phi t. So the rank is less than p plus 1, means there exists coefficient here, lambda t, b1 t, until bpt, such that you have a linear combination of these vectors equal to 0, such that minus lambda t times the gradient of the rho, the function rho, but the gradient of the function rho is just the phi t. The gradient of rho applied in phi is exactly phi plus the sum of bi t times the gradient of fi in phi t. Since the rank is less than p plus 1, there is this constant here for each t, such that this linear combination here is equal to the vector, the null vector for e equal to 1 until p. This is exactly the equation 2. Then you can take the vector b. The vector b is defined as follows. The coordinates of b is b1 until bp, b1, bp, and you take the norm of b. Then you divide the equation 2 by the norm of b. Then you will obtain this equation we denote by lambda t, lambda hat, as in the following way, and b hat as in the following way. Then equation 2 is equivalent to this equation, lambda t hat phi t equal to the sum bi t, the gradient of fi in t, in phi t. The idea here is just to take the equation 2 and divide by the norm of b. Then we obtain the equation 3. Now the idea is to take the model, the norm for both sides. Then you take the norm here and the norm here and the norm in the right side. Then you multiply by phi, the norm of phi in both sides. We obtain square key here, and then the product of that with the norm of phi t. Since the norm of b hat here, the norm of b hat here is equal to 1, then this expression is greater than or equal to v in of the Jacobian of f in phi t. This is greater than v, the Jacobian of f in phi t, because the function v here, we take the minimum of all b with norm equal to 1. Then now the idea is to prove that this converts to 0 Consequently, here is the norm of phi t. Consequently, this expression converts to 0, and you obtain that C in K infinity F. So the next steps is to show that this converts to 0. Okay? To do this, you take now this equation, the sum of bi hat with the derivative of the composition of Fi with phi, derivative with respect to t. Then this, by the Chern rule, is exactly that. But this, from the equation 3, is exactly lambda hat phi t. So you can replace this by lambda hat. So for we obtain lambda hat phi t product with phi prime t. But this is just you take out lambda hat. This is just the derivative of the norm of phi t square. Here the derivative. So if this, in other words, here we use the equation 3, and we obtain this expression. Now, since when consider Fi applying the curve phi t from the hypothesis, this converts to Ci. In particular, this implies that this analytic curve has order non-negative for each I. And since the norm of B hat is equal to 1, then this product here, the order of this analytic curve is non-negative. Consequently, the order of this curve is non-negative. So the order for the order of this analytic curve is non-negative. Consequently, when you take the norm of phi t, since the order of phi t square is greater than the norm of the derivative, the norm of this expression is greater than 0. If the norm is greater than 0 of this analytic curve, then this curve converges to 0. So this curve converges to 0. It means that this curve converges to 0 when t converges to 0. In particular, we obtain that this converges to 0. It's just this expression here. So we obtain that this converges to 0. In particular, from this inequality, we obtain that the V of the Jacobian of F applied at phi t product with the norm of phi t converges to 0. From the definition of K infinity F, we obtain that C is in K infinity F. The goal is exactly that. This finishes the idea of the proof. The inclusion in the theorem, we remember here the inclusion as AF is a subset of K infinity F can be proper by the next example. From an example from Paunescu-Zaharia. you consider a polynomial mapping from R3 to R, then for this polynomial function, you have that 0 is in K infinity F, but 0 is not in S infinity F. In other words, S infinity F for some class is a better approximation to the bifurcation set than K infinity F. Another result related to S infinity F is on vibration field. So given a polynomial mapping, then the bifurcation set is a subset of the critical values union with the S infinity F. Moreover, both sets are closed sets, and we can use, for instance, the Kurdyka-Simon field to obtain that both sets are semi-algebraic sets of dimension less than p. In particular, this set has measure 0. Consequently, the bifurcation set of real polynomial mappings has measure 0. The idea to prove this inclusion is to use vector fields. You can define some with the condition S infinity F. We can define some vector fields and to obtain the trivialization for F. Here is some reference, and I stop here. Thank you. Question, remarks, or welcome. Okay, thank you.
Okay, so I'm told I'm green. So maybe let me start by saying that my lecture was intended as a follow-up lecture. So what I presented today was an overview of the lectures posted online. If you go to the conference website, there is a link to a folder that contains 6 hours of recording videos, handwritten notes, PDF of a paper I wrote about this, and so on. So if the topic interests you, of course, if you haven't seen it before, perhaps what I said today would be difficult to follow, but if the topic interests you, I'm still around for this week and next week. Please have a look at the videos and let me know if you have questions about, problems related to this story. Now, as a general advice, perhaps, again, if the topic interests you, there are a bunch of experts in the audience that you don't meet on a regular day. So I would advise all the young people to actually take this opportunity to actually bug these senior people and ask for good questions, good problems to work on, and so on. So this is your chance to actually go a little bit beyond your usual graduate studies. All right, so again, since some of you haven't seen the notes before, maybe they're not advertised or you're not aware of them, let me actually do some hands-on calculations. And I want to first justify this formula for the Euler characteristic of a non-singular projective hypersurface, and then we'll have some more concrete examples once I'm done with this. So I more or less indicated this in the lecture today, but I can do it in more detail now. So the story here is this, right? So I said that non-singular hypersurfaces have their topological or even diffeomorphism type determined by the degree. So can assume without any loss of generality, so this is a standard abbreviation, without loss of generality, can assume that F is in fact given by the sums of d powers of coordinates. So x0 to d plus x1 to d and so on. Xn plus 1 to d. So it is enough to work with, if you look at just this polynomial as defined on Cn plus 2, of course it has a singularity at the origin, but since we take the corresponding projective hypersurface, the origin is not allowed. So this would be a non-singular degree D hypersurface. Okay, so now another thing I said is that the Milnor fiber, so this is the Milnor fiber, for such a polynomial, which now I regard as a polynomial on the affine space, so let me write it like this. In Cn plus 2 with values in C, having only an isolated singularity at the origin, the Milnor fiber is a bouquet of spheres. Well, I should write it like this. So the Milnor fiber is homotopy equivalent to a bouquet of, well, this is a wedge of n plus 1 dimensional spheres. How many? Well, how much the Milnor number is. So now in yesterday's problem session of Dirk, you saw how to calculate some Milnor numbers. In this case, the situation is very simple because we have sums of polynomials of different variables, and there is a result called Thom-Sebastiani, which tells us that it's sufficient to understand the Milnor fibers for each of the summands and then take some topological join of that. If you haven't seen that, again, this is something that you find, for example, in Dinka's book, very well explained, even in, I guess, Milnor's book, Milnor's old book on the topology of hypersurfaces. So in this case, the Milnor number is really, I take the Milnor number of any monomial. The Milnor number of such a monomial is, well, what's the Milnor fiber for x to d. Well, x to d is equal to 1, which has d points in it, right? And how many of those I have? I have n plus 2 such. But remember, yeah, I guess what am I saying here? D points, but I have to throw the Milnor fiber is D points, but what is the reduced homology? Is D minus 1 points, right? For the Milnor number, I need the reduced homology. So D minus 1 is what I get from each of the summands. And how many summands I have? I have n plus 2 summands. So what you get here is n plus 2. All right. So what we get on the nose from this is, for example, the Euler characteristic of the Milnor fiber being, well, 1 coming from degree 0. And then in degree n plus 1, you have this d minus 1 to n plus 2. All right. Now, this is not what we wanted. We want the Euler characteristic of V, okay? But what I said earlier today was that the tautological map from the Milnor fiber to the complement of V, so this is just, this F is in, what is it? It's in Cm plus 2, right? So I have the same coordinates, x0 up to xn plus 1, and I map this to the equivalence class of that point. This map is D21, is a default covering. Covering map, I should say. The Euler characteristic is multiplicative for coverings, so this will tell me that the Euler characteristic of F, which we know already, is D times the Euler characteristic of the base of the covering, CPM plus 1 minus V. And the only extra information I need is that this Euler characteristic of the complement is just the difference of Euler characteristics, because the Euler characteristic in the complex world is additive. So what I have here is the Euler characteristic of CPN plus 1 minus the Euler characteristic of V. And of course, the Euler characteristic of CPN plus 1 is n plus 2. So putting everything together, let me write it one more time. What do we get? The Euler characteristic of F was 1 plus minus 1 to n plus 1 times d minus 1 to n plus 2. And this is, I look at the right-hand side now here, d times n plus 2 minus the Euler characteristic of V. Solve for the Euler characteristic of V, and we get what I wrote up here. So this is a way of finding the Euler characteristic of a smooth hypersurface using the Milnor fibration. There are other ways using Chern classes and so on. This is not a unique way of doing it, but this is more related to the topic of this school. Are there any questions? I'm only using two elementary things, that the Euler characteristic is multiplicative for coverings, for finite coverings, for covering maps, and it is additive. It is what's called motivic. Of course, I also used Tom Sebastiani when I calculated this Milnor number. This is something that perhaps you'll see repeatedly in lectures about the Milnor fibration. Questions? Yes, go ahead.
Hi.
Yes.
So
Okay.
you have a global Miller fiber.
Yes. So there is, because of the homogeneity of the polynomial f, the Miller
Okay.
fiber, the Miller fibration is global, right? So Cn plus 2 minus this affine cone fibers by the function f itself. So the fiber is what we call f, the global Miller fiber. This is also called affine Miller fiber or something like this.
Okay, thank you.
Yeah.
So you can obtain the same Milnor number by this deformation Milnor number I explained yesterday for x to the power 3 plus y to the power 3.
Right, yes. So you can, yeah, calculating the Miller number, here I did it by Tom Sebastiani, but you can deform and count Morse points of a deformation. All right, so now what is this degree genus formula? So this is something you see in the first course of algebraic geometry, perhaps. But you can get it immediately from this kind of calculations. Why? Because, well, if I work with a Riemann surface or projective curve, this is really, the homotopy type is, you have a two-sphere to which you attach some handles. How many handles you attach is exactly the genus. Each handle will give you one hole. The number of holes is the genus. So the Euler characteristic on the one hand, it is 2 minus 2g. So each handle has a meridian and a longitude. And the 2 in front comes from degree 0 and degree 2. And on the other hand, it is given by this formula. So 2 minus 2g is equal to this, whatever this is. So let's write it down. So on the one hand, it is this, what I wrote here from just, I don't know, Riemann classification of surfaces, if you like. So Riemann surface. On the other hand, it is, well, let's see, n is 1. So we have 3 minus 1 over d. Okay, now, n is 1, so this sign disappears here. So I have 1 plus d minus 1 to power 3. Do the calculation and you'll see that we get exactly what we want. I mean, this is not, let's see. So let me do just this calculation. Oops. So what do I have here? 1 plus d cubed minus 3d squared plus 3d minus 1. Cancel the 1s, cancel some d's. 3 minus 3 after canceling the d also disappears. So what we really get here is minus d squared plus 3d. I hope I wrote it correctly. So 2 minus 2g is equal to minus d squared plus 3d. Solve for g and you get your formula. You can start plugging in degree 1, degree 2, and so on, see what genus you get. I know Cesar likes that exercise. All right, let's not do that here. You can do that yourselves.
So it's interesting to see that for d is 1 and d is 2, the answer was.
You get a sphere, yes.
So the answer is the same.
Yes. Okay. Now, this example, if I saw it without knowing anything about the topology of the hypersurfaces, I would have found it very surprising. Why the topology, some topological invariant dictates the algebraic structure of the hypersurface. Of course, that's not generally the case, but in this situation it is, right? So all I'm giving you is the Euler characteristic, which is such a simple invariant. And what I'm getting in exchange is the algebraic structure of the hypersurface. So these kind of results are quite powerful, and this is not what one should expect typically when you look at the topology of complex algebraic varieties. Though, of course, it's nice to have something like this. So, well, in this case, all I have to do is to plug in the formula. This is the formula. I equate it to n plus 1. And then I look, well, what options do I have, right? And actually, does anyone want to try this to see how it works? It's a very, very elementary calculation. I'm just afraid I may get it wrong. Have you seen this before? Let's say, I don't know, we can do it. So the Euler characteristic on the one hand is n plus 1. On the other hand, it is n plus 2 minus 1 over d, 1 plus minus 1 to, n plus 1, d minus 1 to n plus 2. Okay, we cancel an n plus 1, move some things on the other side. So 1 is this thing with 1 over d and so on. So how about I multiply everything by d? So d equals what's in the parentheses? 1 plus minus 1 to n plus 1 times d minus 1 to n plus 2. Well, okay. Now let's plug in n is even, n is odd, and see what you get. So n even. What do I have? We have d equals 1 minus d minus 1 to n plus 2. So, well, I can move some things around, right? So d minus 1 equals minus d minus 1 to n plus 2. Okay, now, you see any problem here? So d is the degree, d is at least 1, right? N is even. Well, that's less important here. So the left-hand side is non-negative. The right-hand side is non-positive. Of course, you cannot have that unless they are both equal to 0, right? So in this case, d has to be 1. And, well, for the other case, something similar happens. Let's see. In this case, let me write it again as d minus 1 equals. Now, n is odd, so this sign disappears. And I have d minus 1 to n plus 2. Okay? I would like to cancel a d minus 1, but for that I have to make sure d is not 1. So that's, well, or just take a common factor, right? Sorry if this is too elementary. I was told I should be elementary, so that's what I'm trying to do. So let's be elementary. So I'm moving things to one side. So d minus 1 times 1 minus d minus 1 to n plus 1 equals 0. well, so now I have two cases, right? So from here, D is 1, or from the other side, remember D is still D and N are integers, right? No negative integers. So for this to happen, the only possibility is that D is 2. Okay, so these are some exercises that we had on the slide earlier. Are there any questions? Okay. Now what I want to do is to, I think I have time. What I want to do is I want to show you some geometric interpretation of the Euler characteristic for hypersurfaces with isolated singularities. And then let's work out some special situations, right? So now I'm going to remove non-singular, and I'm going to ask isolated singularities. Of course, then this formula is not true anymore. And the question is, why not? I mean, what goes wrong? Okay, so let's take our naive picture of a hypersurface with isolated singularities. And let's put near it a smoothing. So we saw earlier in the lecture that one could create a family with the nearby hypersurface being the nearby member of the family being smooth. Okay. Now, what do these things have in common? Well, they have a lot in common, but also have things that differ. I'm going to take small balls around the singular points in the ambient space. Okay, here I cannot take it that small, but so these are the Milnor balls, so to speak. And now I notice, at least from this naive picture, that what's left out of these balls has the same topology. So the red pieces do not differ from each other in the two hypersurfaces. All the changes in the topology happen in these Milnor balls. So now if I want to calculate the Euler characteristic, so one thing you perhaps heard in the lectures is that algebraic varieties, in particular hypersurfaces, are locally contractible, right? So this part of the hypersurface inside the ball, yeah, I don't know how, maybe I should, let me just simplify the pictures as much as possible. Let's not complicate the matter too much. Let's make everything look like cusp. So the part of the singular hypersurface inside the balls is contractible. So when I look at the Euler characteristic, I said this is additive. So the Euler characteristic is going to be made of the hypersurface V, or now this is V, yeah? And Vt would be the smoothing. So the Euler characteristic of V is made of the Euler characteristic of the red pieces plus a 1 corresponding to each Milnor ball. While the Euler characteristic of Vt, of the smoothing, is going to be, again, the Euler characteristic of the red piece plus, okay, now I need a color that you can see. Let's see which one I should. Green. Can you see green? Does it look too much like yellow? All right, so what do I do in the Euler characteristic calculation? Passing from V to VT or vice versa. I'm swapping the parts in the Milnor ball for each other. But what are the green parts? Does anyone see what the green parts represent with respect to the singular points? What? I didn't hear that yet. Yeah, what does it mean, a stabilization? So these are local smoothings, right, of singularities, of isolated singularities. How do we call those? What? Milnor fibers. Aren't they Milnor fibers? This is not the resolution. I'll give you an example in a minute with the difference between a smoothing and a resolution. So what I'm doing here, I'm doing local smoothings of singularities, essentially. Local smoothings are the Milnor fibers of those singularities. These are isolated singularities. So all I'm doing in the calculation of Euler characteristics for hypersurfaces with isolated singularities is that, well, as I said, away from these balls, things are the same. But then in the balls, I'm swapping these contractible pieces of V by the corresponding Milnor fibers. So I'm trading, let me write this very informally. So the Euler characteristic of V is really made of, let's say, the Euler characteristic of V minus the singular locus plus the Euler characteristic of the singular locus. And I said the singular locus, of course, are just these points, but I can move a little bit more inside of a Milnor ball because these pieces are contractible. They have the same topology of the points. Now, if I look at the smoothing, that's the Euler characteristic of the smoothing minus the union of these Milnor fibers. I don't know how to call them here. Let's say green parts, plus, I'm adding this back, the Euler characteristics of the green parts, the union of those. All right, so if I want to compare these two guys, these pieces are the red pieces. They are going to have the same Euler characteristic. So these two guys are equal. And the only difference comes here. What are these green pieces? These are the Milnor fibers, local Milnor fibers. Now, for each singular point, I have a corresponding Milnor fiber and its Euler characteristic. The difference of these two guys, of course, is going to lose the contribution in degree 0, right? That's why you end up with the reduced homology of the Milnor fiber. That's why you end up with just the top homology of the Milnor fiber. So chi of V minus chi of Vt equals, well, the sum over the singular points of V. What? The Euler characteristic of that point, which is 1, minus the Euler characteristic of the corresponding Milnor fiber at this point, x. So each of these green pieces is a Milnor fiber. If this was x, this guy here is going to be fx, corresponding Milnor fiber. Now, what is this? Well, let's calculate it. So 1 minus, well, the Euler characteristic of the Milnor fiber. What is the Milnor fiber of an isolated singularity? This is a singularity now in Cn+1 locally, right? So each of these Milnor fibers has the homotopy type of a bouquet of n spheres. How many? Mu x, whatever mu x is, but mu x is the local Milnor number. So I have 1 minus, now 1 coming from degree 0 plus minus 1 to n times mu x. Okay, so the Euler characteristic of V is equal to the Euler characteristic of the smoothing. So V being now isolated singularities. So the Euler characteristic of the smoothing, which we know is this guy. I calculated it earlier. This is a smooth hypersurface. We cancel the ones here, and we have plus minus 1, well, sums. I can put minus 1 to n plus 1, sum over the singular points, corresponding Milnor numbers. Of course, you can do this with vanishing cycles and all of that I put on the slides earlier, but in this case, things are much simpler and you can just do simple-minded additivity of Euler characteristics. Yes, go ahead.
So don't you need some condition on the, I don't know, on the connectivity of the sets to apply the additivity of the Euler characteristic?
Yeah, the Euler characteristic is additive in the complex world. This is what I said.
Okay, thank you.
Yeah. You're right. This is the key here. But
So the Euler characteristic does not depend on the position of the
yeah, the Euler characteristic does not. Yes. But the Bethe numbers do, as we saw, right?
But in this case, I think by cutting with Milnor bolts, you kind of leave the complex world because the Milnor fibers are not complex analytic subvarieties, right? But I think you could fix it by using relative homology and doing it relative to the Milnor bolts.
Yeah, you know too much. I'm cheating a little bit, but
Okay, sorry. No, but there are ways to assure
yeah,
the
there are ways to
additivity here.
fix this, but I don't want to get into technicalities because that
Okay.
kind of defies the purpose of this picture.
So you need, you have also exercise session after this, or is this tomorrow? Okay, so then we but we are not finished now. I think.
But if you take a slightly bigger green part, then you have to apply the Euler characteristic and take away the intersection, and then you get something completely different. And the Euler characteristic of the green part is still the same, and the red part is
No. Yeah. So the size of the Milnor ball, of course, it's meant to be the Milnor ball, right? So after a certain threshold, it doesn't matter how I change the size. The Milnor fiber does not change its homotopy type.
Yeah, but the two sets are whatever. Thank you. Anyway.
No, you see, it's the same as here, right? So here I'm really saying I take out the points, but then I say homotopically the point is just like the inside of the hypersurface inside of the Milnor ball. You know, these are the typical homotopy theory arguments. Yes.
Well, I want to ask you about the index of those singular points.
Mhm.
I don't know if, well, this theory is so similar to some topics on differential equations. For example, the red lines, we could be that we can apply the tubular flux theorem in regular parts, and in the centers we can do a regularization, something like that. But
I see what you're saying. Okay.
yeah, but I want to ask you about the index, if this method of Milnor fibers is useful, for example, to determine the topological index, the elliptic and hyperbolic gradients.
This is beyond my expertise. Maybe. I can't really. I have to understand the question first to be able to answer it. What I want to say is that this is the way that Goreski-McPherson construct the specialization map. So I told you there is a map from the smoothing to the singularity. And that map sends the red pieces to each other diffeomorphically, and it sends the green pieces here to these points. So the topology of the green pieces, these are exactly this sphere. So these are the vanishing cycles locally which get killed under the specialization map. Okay? So this is the
Yeah, in that part, it's like you remove the point. Yeah, I asked that because of the Karateori conjecture also to determine the index. But
yeah, I don't know which index are you talking about. So I have maybe we need to talk about this to figure out what you really mean by index.
Okay, let me remind that the same picture will come back in my Monday or Tuesday lecture. And so from the point of view of logistics, between this exercise session and the next one, how long are you going to continue?
I have 5 more
When do you
minutes.
want to start?
No, I have 5 more minutes. I will finish this example and that's it. So I want to actually do an example for this because it's a classical example, and again, it appears in many things. Since someone said the resolution here, I want to actually make sure we understand the difference between a smoothing and a resolution. So the exercise I have in mind is this. So take our V to be defined by this polynomial. I'm not going to ask you what it is for now, though maybe I should. So it's a curve. It's a cubic curve. If you actually work out the singularities, take partials and see where they vanish, you get a point. Call it P. So it's the point 0, 0, 1. If you actually try to draw a picture of this, you'll see your familiar pinch torus. Okay, let's draw the picture. So this is a very nice and classical example, and I wanted to do it in detail. So this is P. Here I have a meridian, and then I have a longitude. So let's draw the meridian here. And then let's draw the longitude. All right, so this is our V. I want to calculate its Euler characteristic, but not only. I want to understand the topology of this thing from different points of view. So let's say you want to remove this singularity. There are 2 ways of doing that, right? So first you can say, well, I can replace this point P by something like this. So I get a torus. And now I restore this longitude here. Or I can do something like this near P. So I get this. Now, of course, I don't have the longitude anymore, but I still have the meridian. Now, This part here basically replace the point P by this meridian. Oops. So if I look in the neighborhood of this point P, and I see what I get in a neighborhood here, I get exactly this circle, which under this map gets squished back to the point P. So this is what we call a vanishing cycle. In fact, this is the homotopy type of the Milnor fiber. Now, what is this? Well, this is a normalization. This is a resolution of singularities. So here I have smoothing, or if you like, specialization, and here I have normalization. Or resolution, if you like, in this case. All right, so
Point to P on normalization.
I could
Yeah.
what?
The point P on the normalization gives 2 points.
Yeah,
If you draw
so-
them, it's clear.
Anyway, this is a sphere, right? So this is a two-sphere. But this point gets replaced by these two guys. Okay. By a P0. Not by P0, by whatever, by 2 points. All right, so what is the homology of this guy? Let's do it, of this V. Well, you can tell without anything, right? So H0, let's say with Z coefficients, well, of course, is Z. That's the same as H2 because this is irreducible. And what is H1? I could do homology, let's say, it doesn't matter. Let's do homology. So what is H1? Well, it's also Z, it's generated by the longitude. Why by the longitude? What happened to the meridian? Well, the meridian is a boundary, half of this picture, right? So in homology, disappears. So the Euler characteristic, you do the calculation, the Euler characteristic of V is 1. 1 minus 1 plus 1 is 1. Can we see this from this formula? Yes, of course we do. Why? V has only one singularity, which is nodal, looks like this. Local Milnor number is the number of vanishing cycles there. It's 1. So plug in our formula. So by formula, what I get is that the Euler characteristic is, well, n is 1, so 1 plus 2 minus degree is 3, 1 over 3. 1 plus 3 minus 1, so 2, 2, 3. And then, again, n is 1, so this disappears, plus the Milnor number. Something is off here. No. So this is 3. This is 9 divided by 3. 3 minus 3 is 0. So we get mu p, which was 1. So you get the same formula. Of course, you shouldn't expect to be this lucky to be able to calculate the Euler characteristic by first calculating the homology. You usually try to do it the other way around. But it's very useful case by case to have ad hoc methods to calculate homology of any given space, right? In this case, it's very geometric, but we'll see maybe in some other exercises on Friday that you have to use a little bit more algebraic topology to do calculations by hand. All right, so I'm done. 45 minutes, that's the end. Questions? Any questions? Yeah, go ahead.
Well, for me, it is still a little difficult to understand why the green part of that diagram it represented a Milnor fiber, actually.
Well, so how do you define the Milnor fiber? You take a small ball around your singularity and you intersect it. Sorry. Yeah, so let me actually draw the picture since this is, all right, I do it here.
Explain the A1 singularity.
Yeah, so here I did the A1 picture, right? So I take a little ball around your singularity, and now, well, let's see. So the link of, do I have to say the link? Maybe not. Actually, maybe want to actually write down what the Milnor fibration, how the Milnor fibration looks for you.
Shall I do it for you?
What's that?
For you?
Yeah, sure. You're the expert here.
Okay. So the local equation can be put as xy is equal to 1. It's one of the equations of the double point. And the best thing is to take polar coordinates now. So r and s times I psi is equal to 1. So for the real part, for the radius part, you have rs is equal to 1. And for the other part, you have phi plus psi is equal to 2 pi times k. So that means that for the radius part, you have this piece, an interval. And for the angle part, phi and psi, you have such a kind of thing on the torus. So in the torus, you have a circle. And in the other part, you have an interval. So you get a cylinder where the circle is the Milnor fiber, which collapses to a point if the radii are equal to 0. So this is the cylinder neighborhood, which goes to this if the radii are going to 0. So this is one of the way to see the Milnor fiber of the A1 singularity in the curve case.
This portion here gets replaced by this little cylinder. Of course, the homotopy type is just the green circle, as I said earlier. And away from these pieces, things are identical. Of course, this is a real picture, so you shouldn't, I mean, we're trying to kind of simplify the matters here for you to get some intuition. This is not by no means, yeah, maybe perhaps this is this picture or this picture are the complex pictures. Of course, complex curve is a Riemann surface, so this is a true picture. That one is more like, you know, for intuition purposes.
I'm just saying that it depends of the choosing deformation of our curve, our variety V.
Yeah, so I think your question comes from the actual definition of the Milnor fibration. So you can define it inside the sphere from which you take out the link, but you can also define it inside the ball working with a Milnor tube, right? So this thing would be a fibration over a little puncture disk. The preimage is the Milnor tube. And this would be the fiber of that vibration in the Milnor tube. So there are a bunch of versions of this Milnor vibration. They have the same homotopy type, the Milnor fibers, and so on. And I think this is where the confusion comes from.
And still the picture is there. I can also show you the Milnor vibration of the D-infinity singularity. Then you have 2 here, and you get 2 there. So then you get this in your torus. This in your torus. This is also a circle. So it shows you that you have more or less the same picture for the infinite singularity. And so I will need that on Monday or Tuesday.
So I should tell you that Dirk here is an expert in singularities and Milnor vibrations in particular. So if you guys have questions about Milnor vibrations, he's the guy to go to. I'm just an actor here. I'm kidding.
Some other exercises in your story.
Yeah, there will be more exercises. We'll do more, but calculations of hypersurfaces. So I'm kind of taking for granted the picture, the local picture of the Milnor vibrations, which you learn from Dirk's stories, for example.
Okay. This is a good moment to stop the exercise question session and go over in 5 minutes to some other exercise session.